Hi guys, 3.6 on energy is the next lesson. So the definition of energy in physics is the capacity to do work, and energy can be converted from one form to another. And if it changes, a change in energy is what we define work as. So one thing to mention from Science 10 is we did have something in Science 10 called the law of conservation of energy. If you took Chem 20, you probably remember the law of conservation of mass. It's very similar. Energy cannot be created nor destroyed. It can only change from one form to another. So we're going to specifically look in this lesson at gravitational potential energy and kinetic energy, both of which we studied in grade 10. The equations are below the pictures, and let's talk about what they mean. Gravitational potential energy is always going to be the potential of an object to fall and go boom and probably hurt. So anything that will fall due to gravity and hit the ground or hit some other object has gravitational potential energy. So like water at the top of this, oh, I'm blanking. What is this called? Oh, the hydroelectric dam. So the water at the top has gravitational potential energy because if it should fall by gravity to the bottom, it's going to pick up speed. It has a lot of potential to gain speed as it falls. There's Usain Bolt, fastest man alive when it comes to running. I think he's running in the London Olympics, where I believe he set his world record. And that's an example of kinetic energy, kinetic meaning movement. So you can see there from the formula that the two things that contribute to kinetic energy or the energy of something moving are the mass of that object and the velocity or the speed of that object. Let's do an example with potential energy here. We've got a 70 kilogram person who has climbed a 12-meter ladder, and we're going to figure out their potential energy with respect to different things. So it's not always the ground that they might fall and go boom on. They might fall off this ladder and land on the roof. They might fall off this ladder and land on a tree. So we have to figure out how much potential energy, gravitational potential energy, does this 70 kilogram person have if they fall and go boom on these different things at these different reference points? So for part A, they're falling all the way to the ground. So here's my formula. It's pretty simple. mgh is potential energy, gravitational. We've got a 70 kilogram person. We've got acceleration due to gravity. And we've got a height of 12 meters. Pop them in your calculator, and I'm getting 8.2 times 10 to the 3 joules. Since work was measured in joules and work is change in energy, energy is also measured in joules. Okay, same person on top of the same 12-meter ladder, but now we're trying to figure out the gravitational potential energy that they have if they fall, go boom, on the roof, which is 11 meters above the ground. So you might be tempted to use 11 meters in your question. But this is about the gravitational potential energy. How far would this person fall before they go boom? So this 70 kilogram person on Earth, where gravity is an average of 9.81 meters per second squared, would not fall 11 meters if the roof is 11 meters high. The person would fall from 12 meters to 11 meters above the ground, which is only 1 meter that he's falling. So I get 6.9 times 10 to the 2 joules of potential energy there. Falling, the mass is the same, the gravity is the same, but the height that they have fallen is much smaller, so the gravitational potential energy that they have is much smaller. One last example. You can pause and try it on your own if you'd like. 70 kilogram person on Earth fall and go boom, but now they're going from 12 meters high to a tree that is 7 meters below the top of the ladder. English is important. Are they falling 7 meters, or is it like the roof question where the tree is 7 meters tall? Those are saying two very different things. This says 7 meters below the top of the ladder. If you fell from the top of the ladder to the top of the tree, you would go 7 meters. Very important to distinguish between those two. So here we go. Pop this in your calculator now. 70 kilograms times 9.81 times 7 meters. I'm getting 4.8 times 10 to the 3 joules. Now, a pendulum bob, so if you have some kind of Newton's cradle or person on a swing set or something, these are all examples of a pendulum. The bob is just the mass at the end. It's 2 kilograms and it's fixed from the ceiling by a string of length 1 meter. If the bob is pulled 0.750 meters to one side, what is its potential energy with respect to the equilibrium position? So the equilibrium position is in the middle here, this one. What we're doing is we're pulling it all the way back to one side. The length of the string, it says, is 1 meter. Okay, the horizontal distance that it's been pulled over, so here to here, is the 0.750. Okay, now I've drawn that in here so that you can see a right angle triangle. If you have two sides given as numbers on a right angle triangle, what can you do to find the third? I'm going to label it A. Good. Pythagorean theorem. But we're not looking for the hypotenuse. We're looking for a different side. So we're going to use Pythagorean theorem rearranged to solve for one of the sides that's not the hypotenuse. So c squared minus b squared equals a squared. Put your numbers in there. C, the hypotenuse, is the 1 meter. Here's the 0.75. I combined the steps there. You're going to go 1 squared minus 0.75 squared, and then you're going to square root your answer. You can do it all at once if you'd rather. But either way, I'm getting 0.66 for my A value. Now, think about the gravitational potential energy for a second. How far is the pendulum bob going to fall? So that's the height that we need to think about. I'm going to put one more sig dig in here. So the pendulum bob goes from this position to this position. Gravitational potential energy is the straight up and down height that the thing is falling. So it really doesn't matter that the pendulum swings from side to side. It's this height right here that we're worried about. Okay, that's the potential that the pendulum bob has to fall downwards towards the earth. That's how much height, that's how far it can fall because the string is holding it and not allowing it to fall any further. So if we wanted to calculate the potential energy with respect to the equilibrium position, how much potential does it have to fall only as far as the string will allow it? EP equals mgh. It says that the pendulum is 2 kilograms on Earth. Okay, and it only has how far to fall? Well, A was 0.661. Okay, and we want the height here. We know that the whole string there is 1 meter long. So if I wanted just the height, I'm going to take 1 meter and minus, the 0.661 meters that I just found. So I'm going to use a height of 0.339 meters. That's what's going to go right here. That's how much height that pendulum bob will fall with respect to the equilibrium position. I could ask you to find it with respect to other things, like pretend the string breaks. How much potential energy does the pendulum bob have to fall to the floor? In which case you would just use a different height. But this is asking us with respect to this position here. Okay, so that all goes in your calculator. I'm getting 6.64 joules of energy. All right, a 10 Newton ball is accelerated uniformly from rest at a rate of 2.50 meters per second squared. What is the kinetic energy of this object after it has accelerated a distance of 15 meters? So all we know in this question is we know the weight of the ball because it's measured in newtons. So that's actually the force of gravity or weight. And we know the acceleration. So we don't really have that much to go off of here. What we need for kinetic energy, let's just write the formula down. It's 1/2 times mass times speed squared. I don't have the mass right now. I have the weight or the force of gravity. And I don't have the speed. I have the acceleration. And I do have a word that means initial velocity is 0. So I wonder if I could figure out using some of these numbers what the speed is and what the mass is. So this is kind of a 3-part question. I need to find mass, and you can do these steps in any order. And I need to find speed. And then I need to put them into the equation and figure out kinetic energy like the question is asking. So do this in either order, it doesn't matter. I'm going to start by finding mass because I know that my weight, aka force of gravity, is 10 newtons. We assume that this is on Earth because they haven't said any differently. And we should be able to find our mass in this equation. So Fg equals mg divided by g, and you get mass equal to force gravity, which the force is acting down, so I'll put a negative on my force, divided by acceleration due to gravity on Earth, negative 10 divided by 9.81 negative is going to give me approximately 1.02 kilograms. Squiggly line, because that's not what the question's asking for. It's just one of my steps to get to the final answer. Second step, they're saying find V. So here's what I know from the question. Starting from rest means 0 meters per second for initial velocity, accelerating at 2.50 meters per second squared, going 15 meters for a displacement, and I need to find VF so I know the final speed and can sub it into my EK equation. This should look a whole lot like Unit 1. Look at your death equations, your kinematics equations. Pick a formula that has all that stuff in it. I'm picking this one. Okay? Now, something that we can do right off the bat, VI is 0. That term can disappear. I'm also going to go ahead and square root both sides to get rid of this squared. And I get an equation like this. Okay, all of that is just rearranging that we did a lot in the first unit. Now I'm going to go ahead and sub in my numbers. Here's my acceleration. Here's my displacement. Don't forget to square root. 8.66 meters per second is my final speed, squiggly line. Use those two squiggly lines, mass and speed, to now find what they're actually asking for, which is kinetic energy. So put fractions in your calculator in brackets. Better to work with fractions than decimals. Decimals are kind of the lazy man's way out. Remember to use all the decimals that your calculator gave you. Even though we're writing mass to 3 sig digs, it may not be 3 sig digs exactly, so use what your calculator has. Same for the 8.66. The one mistake that people make often with kinetic energy is they forget to square the speed. So you should have the 8.66 sitting on your calculator right now. Just hit squared so that your calculator screen pops up answer squared, and then you can multiply by mass and multiply by 1/2. So when I do this, I'm getting 38.2 joules. Let's try again. We've got an 8-kilogram rock here, dropped from a height of 7 meters. What's the kinetic energy as it hits the ground? I'm going to show you 2 ways that you can do this question. The first way is the way that you're kind of ready to do it. Kinematics, the death equations. This way takes into account that we're dropping this rock from a height of 7 meters. So we know that if we drop it, VI is 0. We know that since it's falling, acceleration due to gravity on Earth is negative 9.81 meters per second squared. We also know that the displacement that it will fall is down 7 meters. We want to figure out kinetic energy at the bottom, and in order to use the kinetic energy formula, we need mass, which we have, and we need speed, which we can find using our kinematics equations. I'm going to jump right to this version. I just showed you on the last example about square rooting both sides of that equation. And I could even have jumped to this not being there because VI is 0 again. So I'm just going to take the square root of 2 times A times D. And I'm going to get a final velocity of approximately 11.7 meters per second. And then I'm going to sub it in to my EK equation. 8-kilogram rock that has a final speed of 11.7 and a final kinetic energy of 5.5 times 10 to the 2 joules. That way probably makes perfect sense in your head. It's what we tend to gravitate towards first. We think kinematics equations because we read the question, we see all of these numbers that we recognize as displacement and initial velocity and acceleration, and we're kind of trained at this point to think that way. Energy takes some complicated questions and can actually make them much simpler. So if we think of the law of conservation of energy, okay, this can make this question actually much simpler. The law of conservation of energy says that energy cannot be created or destroyed, it can only change forms. So objects falling or being dropped are a prime example of this. If I have some kind of object, in this case it's a rock, and I'm holding it up, like let's say I'm holding it at the top of a cliff or something, it has potential energy to fall and go boom at the bottom of the cliff. Okay? Now, when it's at the bottom of the cliff, when it goes boom, how much height does it have? Well, 0. So down here, EP is 0. There isn't any potential energy at the bottom. But I just said that energy cannot be destroyed. So all of the energy that I had up here, which is max, the EP is maxed out at the top. That's as high as I'm lifting this object. That's the most potential energy that I'm going to give it. All of that potential energy, as it fell to a height of 0, was converted to some other kind of energy. We simplify it down in Physics 20. We're not going to talk about any energy lost to air resistance. We're going to say that all of the energy that it had when I was holding it at the top of the cliff was converted to kinetic energy at the bottom. So if it was maxed out up here and 0 down here, that means all of the energy must have been converted to kinetic energy at the bottom. The other thing I know at the top, of course, is that my EK was 0 because I was holding it. It didn't start off with a speed. It didn't have any kinetic energy or energy of motion. So the kinetic energy was 0. The potential energy was all this object had when I was holding it on top of a cliff. And then as it fell, what was happening to the potential was the height was getting smaller and smaller. So potential was getting smaller and smaller. But the speed of the object was getting bigger and bigger. So the kinetic energy was getting bigger and bigger. So as this object falls, there's just this transformation of energy happening. Kinetic is decreasing, or pardon me, potential is decreasing, kinetic is increasing, but if I at any point in time press pause on what's happening here and add the two numbers together, they will always make the same amount of energy. In this question, it's 5.5 times 10 to the 2 joules. That's how much energy this object had at all times during this fall. It always had that much. It just had different amounts of potential and kinetic depending on how far it had fallen, because how far it falls changes the height and it changes the speed. So if I use the law of conservation of energy and I say that I want the kinetic energy of the rock as it hits the ground, I want the EK right here. Well, if I use my logic that I just discovered, it's the same as the EP at the top. This is only because at the top there was no kinetic and at the bottom there was no potential. So all the energy it had at the top was potential and all the energy it had at the bottom was kinetic. So those two numbers, according to the law of conservation of energy, must be the same. So I'm going to use that fact. EP at the top is equal to EK at the bottom. Since I want EK at the bottom, I'm just going to use my formula for EP at the top. You cannot use these formulas interchangeably whenever you want. This only works for this specific scenario where 100% of the energy was changed to EK at the bottom and 100% of the energy started as EP at the top. This only works for certain scenarios. So it's the 8-kilogram rock on Earth, and it was dropped from a height of 7 meters. I can put a negative in there because it went down. So here we're going to get the same number as we got the other way. So law of conservation of energy, it really can be a lot simpler than using the kinematics equations and finding VF so that you can put it into the EK formula. It's just a whole lot more complicated. So law of conservation of energy, if you can remember that, it can really simplify these questions. But you really have to remember that this only works if EP at the top is maxed out and EK is 0 and vice versa at the bottom. EK at the top being 0 just means the object is being dropped, not thrown. Okay. All right, we did some of these, and honestly, they were more complicated when we looked at planets. But by what factor must the kinetic energy increase to cause the speed to triple? So here's my EK formula. I'm going to write it kind of spaced out so I can just smush stuff into it. Okay, there's EK. What they're saying is the speed is tripling. This thing here is getting times by 3. But this thing here gets squared in the equation. So I didn't just change my kinetic energy by a factor of 3. It's not that simple. If I had made the mass triple, sure, it is that simple. But I tripled the speed, which then gets squared, which is actually 9 times the speed. All this other stuff is still in the equation. Multiplication can happen in any order. So I could write this 9 out in front, like that. I'm taking 9 and I'm timesing by 1/2 mv squared. What is 1/2 mv squared? Well, it's the formula for EK. So the question's asking, when you triple the speed, what happens to the kinetic energy? The kinetic energy increases. Now, how would we say 9 times? You could say 9 times, but the more mathematical way to say is it increases by a factor of 9. Okay, that just means it's 9 times bigger. Now, here's your assignment for this lesson, but do not do number 6. We didn't do angled questions with work, and that one has to do with angles. So don't do number 6, but you should be able to do the rest of it. If you have any questions, let me know.